So I will address now the withdrawal times for meat. And Miguel thereafter will address the withdrawal times for milk. We will share this task. And this presentation is about the withdrawal times for meat. We have basically two guidance. As I said, the withdrawal time for meat guidance and the withdrawal time for milk guidance. For milk withdrawal times, you can find these guidelines on the website of the EMEA. And there were two withdrawal time calculations programs on the website of the EMEA, and we could not find them anymore.
Yeah, I mean, we have a new colleague that she downloaded it, probably from the EMEA web, but I don't know exactly where.
No,
but
we have three persons looking for this guideline, and we could not find them anymore. Please check.
I think they are there actually. But the way it's true that the way the guidelines are presented on the website has changed, and I have a feeling now that you have to go to the guideline and it's on that same page, but it's down. It's maybe a little bit more difficult to find, but I believe it is there.
Werner is very clever, so he tried to find it. That's what he told me. Yeah. Okay, this is how it previously looked like. So the statistics for meat is when you have residue data, use a statistical approach whenever this is possible. This is a preferred approach, and nowadays, for at least for new compounds, always a statistical approach is used. And the method for meat is based on linear regression analysis. And we would go for the upper one-sided 95% tolerance limit for the residue, and this should be below the MAL with 95% confidence. And the upper tolerance limit is a percentage confidence limit which is a upper confidence limit for the percentile of the population. So you would say that the requirement is 75% of the population should be below the ML, and you should be 95% confident that this is the case. So usually it's 95% in Europe. FDA would use 99%. So it means if a lot of samples are drawn from the same population, and each time the 95 upper tolerance for the residue is calculated, then exactly 95% of the determined tolerance limit. For 95% of the determined tolerance limit, it is true that at least 95% of the total population shows residue below the limit. So that's what I just said. So you can be pretty sure, which means 95% confidence, that almost all animals, at least 95%, have residues below this limit. It's different wordings for the same. So, and this is a slide from Werner. He told me don't mix up confidence limit, prediction limit, tolerance limit. And he has given an example. So a point estimate plus minus standard deviation for this type of data would be 10 plus minus 3. And the confidence limit, the 95 one-sided upper confidence limit would be 12. So in the end, it would tell you that with 95% confidence, the true population mean is below 12. And this is the equation for this. So, and the prediction limit for the same set of samples would be 16. And the prediction limit would tell you that the next single value sample from the population will be below 16. And the tolerance limit for this example would be 19, which tells us that with 95% confidence, the true population percentile is below 19. So it's sometimes there's a confusion about if this is a prediction limit, is a confidence limit, is a tolerance limit. So they all give you different answers, and it is depending on the equation and on the definition you use, which is the correct limit. And we would use for the tolerance limit, we use the 95%. percentile with 95% confidence, which tells us that 95% that you have 95% confidence that the true population percentile is below the ML in this case. So the calculation model is based on accepted pharmacokinetic principle. We would consider the terminal elimination of the residue, which in most cases follow one compartment model and would be described by one exponential term. And this is the term for the exponential term, and you can transform it in a linear relationship where Ct is the concentration at the time t. Ct would be the concentration which is expected below the ML, and C0 is the concentration at the beginning of the depletion. And if this plot is linear, so this indicates that the model is suitable. So you have here the normal distribution of residue depletion, the residue depletion curve, absorption, distribution, depletion, and you would consider only the terminal elimination when all other processes have ended. And this is the terminal depletion in a logarithmic form, and this is when you transform it. When you transform it, you would have this relationship, which is a linear equation. So this is the natural logarithm. You can also use the logarithm with base 10. So you can, whatever you do, so you get the same result. So you have the treatment, withdrawal time, and food production period. The linear regression requires that the data are independent from each other. That's why we cannot use this for the milk. So the milk samples are not independent from each other because they belong to individual cows. So, but for residue data, this is okay because they originate from individual animals. In theory, you would require 3 animals at 3 data points to construct a linear regression curve. But the guideline 48 recommends a larger number of animals, which is 16, which is also very low. This is for a statistician, these are very low numbers, but these are the numbers we normally get, the animal numbers, 16 at least, and 4 time points. And the residue concentration should be corrected for analytical recoveries, and less than values are typically substituted with 1/2 of the reported limit. That is what the guideline says. So also this is often forgotten, that to correct the values for the analytical recoveries, if this is an issue, if they use an internal standard and perfect analytical setup, so and have 100% recovery, it's not necessary. But if you have 60% recovery, please correct the data before you use it. So that's why I said it's often forgotten that the risk assessors don't normally check the analytical methods for recovery, limit of quantification, what I said, if they use the right sample preparation setup. So this all should be checked so that you can see that the data are reliable. So it is necessary for this model that the relationship is linear for the log transformed data, that the assumption of homogeneity of variances is fulfilled, and that assumption of normal distribution of errors is fulfilled. So these are statistical assumptions that are required to be fulfilled before this model can be used. And first you would do it with what be a visible inspection of the data, plot the data and see if there's a useful linear relationship. And obvious deviations from linearity at early time points may indicate that the distribution is not ended, and these time points may be excluded from the calculation. Deviations from linearity at late time points may be due to concentrations below the limit of quantification. And below the limit of quantification, you cannot observe the kinetics, so you may need to decide if this data should be excluded or substituted or what else. It depends on the totality of the data. And outliers are normally not considered unless there's the clear reasoning for their omission. So the database overall is too small to conclude if observation is an outlier or not. So first you would do a statistical test for linearity. So the usual procedure is comparing the departure between group means and regression line and the departure of the y values from their group means. And the next test would be the homogeneity of variances. So we have different tests at hand. This is all described in the guideline. We would also use the log transform data, and recommended in the guideline is the Cochrane test. And you would check if the distribution of the residues at each slaughter day are normally distributed. So a good inspection, a good test for this is the visual inspection of a plot of the ordered residual versus their cumulative frequency distribution on a normal probability scale. And a straight line indicates that the observed distribution is consistent with the assumption of normal distribution, and this is from the guideline. So these are the ordered residuals, and they fit in a straight line. And this animal is a bit away from the line and might be an outlier. So the guideline says if it's 4 standard deviations away from the guideline, it might be an outlier. So it can be discussed, but in principle, we would not accept outliers. So these are in principle the 4 tests. This is the lack of fit test, the test for homogeneity, and the test for normality of errors. If all this is okay, then you can go ahead with the calculation. So the withdrawal time is determined at the time when the upper one-sided tolerance limit with a given confidence, which is 95-95, is below the MAL. It is proposed to use the one-sided upper confidence limit 95 in Europe with a 95% confidence, and this is the order of this equation. The citation is also mentioned in the guideline. And this is the equation for the. This is an approximation equation. This is also described in the guidance. And this would be the tolerance limit. This is the depletion of the residues. And this is the tolerance limit, and you go along this line and check if this is below the MAL. And then you have 95% confidence that 95% of the animals are below this value. And this is a data set, a real data set, and this has been assessed. And the withdrawal time was 28 days. These are the data. You can recalculate this if you want. So the tests were fine. The MAL was 30. Bartlett test, linearity tests, so all not significant. And the withdrawal time was 28 days. This is an output of the program. And so you have here you have the days, and here you have the tolerance limits, and you just check when it drops below the MAL. It was at day 28. And this is the same data set with an additional day. It was day 1, and here a day 35. So you can see from the additional day that the residues do not fit into this assumption of a straight line, these ones. And these ones are very low because they are below the limit of quantification. The first time point shows lower values than the second. Leave it out. We are only interested in the depletion phase. So the visual inspection would tell you that this is probably a time point which does not belong to the depletion phase. The last time point shows only values below the LOQ. The guidelines would recommend leave it out. And there remain some other values below the LOQ. The guideline would recommend replace these values by half the LOQ, and the FDA would recommend leave these values out. So that's what we would do. We would leave the first time point out and leave the last time point out. And then we have 3 remaining time points. for the same data set. This is the depletion on a log, on a not transformed data. Calculate for each time for the tolerance limit, as withdrawal time shows the first time point at which the tolerance limit is below the ADI. What this is a slice from by such a procedure, not the full information is used. Calculating the tolerance limit for day 28 would ignore possible impact of one high residue at. So I'm not sure what Werner would tell you with this. So to be honest. So this is the log transformed elimination, and though you have to compare the log of 30 with the tolerance limit. So this is linear, normally distributed, and homogeneity of error of variances is fulfilled, no outliers. So there are in principle two methods: the non-central t-distribution, which the FDA would use, and the Stange formula, which I said is an approximation, which would be used in Europe, and normally they give the same results. And this would be the output of the calculation program, which is probably now available on the website again. It is?
It is.
Okay. So sorry,
I can show you.
I was wrongly informed then.
No, it's difficult.
And this is a plot that Werner has done. So, and the withdrawal time would be 28 days. So you have a data set that needed to be modified to have the right result, and we have the second data set which was already okay. So, and this is an output. Werner has calculated its own program, its own matrices in Excel, and show you this. And this is a quite interesting slide. So he has taken 1,000 samples of a size from a certain distribution of a size of 20 and 200. And for each sample, the upper tolerance limit was calculated, and the fraction of the population with a parameter value below this limit was determined. And this is the result for the 20 samples, and this is the result for the 200 samples. And the message is, with increasing the sample size, the mean upper tolerance limit converges to the 95% percentile. So you can see this from here. This is the lower sample numbers, so you have 99s, 98, 97, and here you get closer to the 95% percentile, which means in the end that tolerance limit has a built-in safety span. So the higher the sample numbers, the closer you come to the 95% percentile. So this is automatically, it would punish bad studies, because the tolerance limit get wider away from the percentile, and in the end the withdrawal time gets longer. This is quite interesting. And the next simulation was done with 1,000 random samples with the same normal distribution at 4 slaughter days, and this is the distribution of the withdrawal time he got. So the meaning behind this is you have conducted 1,000 studies, and this is the result from the 1,000 studies. The withdrawal time would be 22 days to 38 days. This is simulation, but reality might be worse.
It will.
So it's equally designed studies for the same residue might result in different withdrawal times. So coming back to the discussion this morning, that's why it's ridiculous for me to say they have a second study that shows a lower withdrawal time. So they all belong to the distribution of the withdrawal times for the same product and for the same study setup. It's not actually that the product is actually better or leading to withdrawal to a shorter withdrawal time. It's just statistical variability, and you can see it from this slide very perfectly. So there's a huge variation even for the same study setup. So I will, yeah.
So this means that variation due to different animals and due to differences in the setup and formulation, that will come on top of this?
Yes. Yes.
Okay.
These are just the same data set, and he made thousand samples from the same data.
Yes, I mean, what he did is with the data, well, I guess what he did is with the data, he calculated the mean of his data and the standard variation of his data, and that, so he had a defined population with that mean and that standard deviation, and he inputs that in the computer, and it gives you 1,000 random samples with that distribution. If that distribution is slightly different for maybe, I don't know, because you are using another breed of cows or whatever, if the distribution is also different, well, you will have more different results than in this case. Oh.
That's true. So I come to some points to consider. Which tissues determine the withdrawal times? Is departure from regression assumptions acceptable? Withdrawal times should be set by interpolation, not by extrapolation. This is the issue of extrapolation. How do we deal with the less than values, values below the limit of quantification? And how do we deal with outliers? And which tissues determine the withdrawal times? The withdrawal time is the program would be run for each tissue separately, for which an ML has been set, and also for the injection site if appropriate. And the longest of these withdrawal time will be considered the regulatory withdrawal time. So extrapolation, what if the resulting withdrawal time is later than the last slaughter day? So generally, again, extrapolation is problematic in linear regression, but we would accept sometimes slight extrapolation because we can reasonably assume that the kinetics will stay linear once we have checked that it's linear. But it's just an assumption. Extrapolation is not a proof. You cannot prove that it's correct. So we would also accept extrapolation since the tolerance limit curve is bent upwards. So it is closest to the regression line in the middle. And then it goes away from the regression line. The longer the withdrawal, the longer the time is. So this is also built in the equation. So you can see it already from the equation that this is the case. Yeah, and thus the withdrawal time would not be underestimated if you extrapolate. So this is what we do. So this is a case-by-case decision, and you can never justify extrapolation because extrapolation is a conclusion that you made without data. You can never say that is correct. But I did. So dealing with less than values, they may have an impact on the withdrawal time. The CVMP would substitute these values by half their limit, and the FDA would omit these values. And Werner has performed a simulation to test different methods to deal with less than values. And 2 more methods were included. So to include the values as they were measured, sometimes values below the limit of quantification are reported. They are not reliable, but they exist in the data files. And you can also apply maximum likelihood approach. And the model that was used was he chose intercept slope and residual variance of a regression line in such a way that the likelihood of observing the measured values. This is the definition of the maximum likelihood. You choose an intercept slope and residual variance of the regression line in such a way that the likelihood of observing the measured values higher than the limit of quantification and the number of values lower than the limit of quantification per time point is maximized. So this is in words complicated. This is the equation for the maximum likelihood. So I will skip this. Can you explain?
Not really explain, but I can give some sort of what I like to think of with when they're talking about maximum likelihood. Because
There are
I'm
some
not, I
slides
have to say
earlier,
also,
I think.
I'm not a statistician
Yeah.
also, but what we do with the maximum likelihood estimations, you create a function that estimates the likelihood of your population or
Yeah.
whatever. And this is the function that is estimating that likelihood, that probability,
Yeah.
so to say. And this function is going to be dependent on various parameters. In this case, the parameters on which it depends, it's the intercept, the slope, and the variability around this line. Okay, so what we need to do is find the values for these parameters that will maximize the likelihood of this function. So what we need to see is which values of these parameters will make the highest value once you calculate all that formula, and that is done with mathematicals, with the derivative and all these things, and you can calculate which of these values will make the highest value for this function.
Yeah.
And then you have the maximum likelihood estimators for these three values, and that the three values that we will use to build our regression line,
Yeah.
I guess.
This is what is said here.
Yeah, it's more or less what it is. So in this case, what we need to maximize is we want to maximize the likelihood of having the values that we have observed above the LOQ, and we also want to maximize the number of values that are below the LOQ.
Yeah.
That in our case, we have 6 values below the LOQ. Where we want to maximize the likelihood that our regression line will have 6 values below the LOQ. And I guess this is how I think about maximum likelihood estimators. Maybe not 100%
This is a
accurate.
good explanation. Yeah.
Okay.
You gave a good explanation.
Yes, but it's how I think about it.
Yeah.
Probably a statistician would give a better explanation about it.
So this is the reference model that has been used. It was a realistic data set, and Werner took the intercept, the slope, and the standard deviation of the linear regression line, and calculated the real withdrawal time, the true withdrawal time. So this has no variability. This is as it is. It is a slope, an intercept, and a standard deviation. And so you can have a true withdrawal time then. No tolerance limit is necessary, since the withdrawal time is not estimated based on a random sample, but we know how long it is. So we know in this case exactly this is the true withdrawal time for the timer. This is a model. We are 100% sure that the withdrawal time is correct. And then you would do simulations. You fix sample size per day and choose slaughter days and fix LOQ and ML and generate randomly residues for each type of slaughter days according to the distribution of the model. And for each of the 4 methods that I've used, omit the data, set them at half the LOQ, do the maximum likelihood, what was the other one? Substitute it by the existing values. You use this method and you do it many times. And then for an appropriate withdrawal time, for the appropriate method, then the fraction of the simulation runs with the withdrawal time method to the real withdrawal time should approximately 95%, according to the definition of the withdrawal time, the definition of the confidence interval. And then the result was as follows. For each of the tested values, omitting of the data was generally conservative, which is clear. This increases the withdrawal time. Omitting the data below the LOQ increases significantly the withdrawal time. And the other 3 methods were rather similar to each other. The percentage of 2 short withdrawal times ranged from 3 to 7%. And the median estimated withdrawal times were always larger than the real withdrawal time, generally by 10 to 20%. And substituting the values below the LOQ by half the LOQ seems to be an appropriate method. And this is the output of this. This is the true withdrawal time, and these are the data for the different simulations. This is The yellow one is the maximum likelihood. The gray one is as observed values. What is it? Orange is the substitution less than half the LOQ, and this one is not considered, the blue one. And the blue one gives much longer withdrawal times. And here is the median is quite similar between the three methods. And this would be the median for the the values not omitting the values, exactly, not NA, I was reflecting what N. This is the true withdrawal time. So in the end, in this simulation, it did not matter which method you used. And it was a number of simulations, about 1,000 simulations, and with different proportions of values below the LOQ. And so, this was an experiment which we did, and this showed that for under practical aspects, it does not really matter. But this is a preliminary assessment. This is not the final assessment. We wanted to continue with this, but it's very time-consuming in the end to do all this simulation. But it was the first impression that we are not on the wrong track with this half the LOQ, not totally on the wrong track. So the alternative approach to establish withdrawal times can be used when data do not permit the use of the statistical approach. One approach for the problem selection of the time point when the concentration of residues in all samples are below the MAL, and a safety span would be 10 to 30% to reach the MAL in all samples. Or you can also use depletion half-life, 1 to 3 half-life. So this is what the guideline says. This is a very rough estimate of the withdrawal time. So why would we not always use the alternative approach? It's so convenient and so simple. So the reason is choosing the withdrawal time at the first time point such that from this time point forward, the concentration of residues in all samples stay below their MAL. I don't know what this means. But now it gets interesting. So this is an evaluation of 62 residue depletion studies. They were analyzed by the statistical and by the alternative approach, and using a safety span. And this is the result. So for 29 of the 62 studies, the usual safety span of up to 30% would have been too short, the withdrawal time. For 1/3 of the study, and this has been done by Johan Schäferli or colleagues from him, and this was normally the case for short withdrawal times. So in 29 of 62 studies, the usual safety span would lead to too short withdrawal times. The 30% safety span is the maximum safety span. But you can see here for most of the studies, so it would be fine. So it goes from 10 to 30, and then it gets longer than 30. All these are not correct when you use the statistical approach. So this contradicts a bit the assumption that the alternative approach is safe. So, and this one you would probably show this.
No, I took that out.
Can
also.
I?
Yes, yeah, you can.
Yeah,
say
Ken.
yes,
So
yeah,
this is the
that.
slide for the tissue withdrawal times. You have this regression line. It's a relationship concentration versus time. And also here, this is a horizontal tolerance limit on the time axis. And this is the tolerance limit here would be on the concentration, and here it's on the time.
Yes,
This is the main difference, but this is just to show it. But you will continue and explain it in better words.
No, I can just in 1 second. I will say, because I won't have this slide. I took some of them, but I left this.
found it so nice that I
Yeah,
wanted to show
I left
it,
this
yeah.
one out
Yeah.
because the difference is that when with the tissue withdrawal period and other milk methods, what we do is we apply the distribution on the concentrations, and that's why
Yeah.
we are having this vertical distributions. But when in the TTSC, we are applying the distribution on the time, not on the concentrations, and that's why we have
Yeah.
this different approach.
So this is on the
It's
time
nice
and this
to
is on the concentrations. Yeah. This is the main difference. But in the end, it's all tolerance limits.
Yeah.